In this video, we're going to continue talking about acceleration in special relativity by talking about Bell's spaceship paradox. Bell's spaceship paradox will lead us to inventing Rindler coordinates, our first set of curvilinear coordinates in this relativity series. Bell's spaceship paradox is one of many so-called paradoxes in special relativity, like the twin paradox and the ladder paradox. At first, these paradoxes seem like contradictions that indicate flaws in special relativity, but more careful thinking reveals that there is no paradox at all and special relativity works just fine. Bell's spaceship paradox works like this. Let's say that there are two spaceships some distance d apart. There is a string that ties the two spaceships together. The string is exactly long enough to cover the distance between the spaceships. If the spaceships move even slightly further apart, the string will break. Einstein is standing stationary halfway between the two spaceships, and sends a light signal to each one, which tells each ship to begin accelerating to the right. The spaceships will both accelerate in the same manner, so that they are always traveling at the same velocity according to Einstein, and the distance d between the ships never changes according to Einstein. The question is, does the string between the ships break? Some people might argue that the string will not break because the distance between the two ships does not change according to Einstein. Others will argue that the string does break because once the string starts moving, it will undergo length contraction, and that it will become too short to cover the distance d between the ships and snap. So which argument is correct? Does the string break or not? Let's first examine this problem with accelerating spaceships in Newtonian physics. You should already know that in Newtonian mechanics, an object traveling with constant acceleration travels in a parabola curve, which looks like this on a spacetime diagram. Now let's look at a pair of spaceships that are stationary some distance d apart. If the spaceships start accelerating to the right with the same acceleration, then their world lines in spacetime would look like this. The parabolic world line of the blue spaceship in front is an exact copy of the parabolic world line of the orange spaceship in the back, just shifted to the right in the spacetime diagram. A stationary observer would see the distance d between the spaceships remain the same throughout their journey. And since this is Newtonian physics, time and space are absolute quantities that everyone agrees on. This means that all observers agree the distance between the spaceships stays the same. Now let's consider accelerating spaceships in special relativity. Remember from the previous video, an object traveling with constant proper acceleration in special relativity travels on a hyperbolic curve, which approaches the speed of light but never reaches it. Let's again look at a pair of stationary spaceships that are some distance d apart. If both spaceships start traveling to the right with the same proper acceleration, then their world lines are hyperbolas that are exact copies of each other, with the front ship's world line shifted to the right compared to the back ship's world line. Once again, a stationary observer would see the distance d between the spaceships remain the same throughout their journey. However, this is now special relativity, and distances are now relative. Recall in the last video that we said a curved world line measures time and space using a different spacetime basis at every point along the curve, where the time basis is tangent to the curve and the spatial basis vectors are orthogonal to it. According to these instantaneous reference frames of the rear spaceship, the distance between the ships becomes greater than d. The ships are moving farther and farther apart from each other, according to the rear spaceship. Now, let's change things slightly. Let's say that we want the spaceships to remain the same distance d apart, in their own reference frame, even as they are accelerating. So the blue spaceship in front must always be a distance d in front of the orange spaceship in the back. Then the front ship's new world line would look like this. It is no longer an exact copy of the rear spaceship's world line. In fact, it is less curved. This means that, in order to maintain a constant distance d between the ships in their own reference frames, the orange ship at the back must accelerate harder than the blue ship in front. Because of this, a stationary observer will see the orange ship at the back catching up with the blue ship in the front, with the distance between the ships getting smaller and smaller, even though the two ships see themselves at a constant distance apart in their own reference frames. So in the first scenario, where the stationary observer sees a constant distance between the ships with equal proper acceleration, the observers on the ships see themselves moving apart, and so a string between them that's moving along with the ships would break. But in the second scenario, where the ship at the back accelerates harder to maintain a constant proper distance between the ships, the string doesn't snap because the distance between the ships doesn't change. The stationary observer sees the distance between the ships get smaller and smaller. This is the resolution to Bell's spaceship paradox. The string will break if the ships accelerate with the same proper acceleration. But if the ship in the back accelerates harder in just the right way, the distance between the ships stays the same in their own reference frames, so the string doesn't break. We can use the idea of maintaining the same distance between accelerating spaceships in their own reference frame to create a curvilinear coordinate system called Rindler Coordinates. Rindler Coordinates show us how time and space are viewed from the perspective of an observer that is traveling with constant proper acceleration. This means that Rindler Coordinates are a spacetime coordinate system for a non-inertial frame of reference. To create the coordinate system, an observer on an accelerating spaceship needs to know how to measure distances in front of and behind them. Instead of looking at two accelerating spaceships, let's look at a whole train of accelerating spaceships. Each ship will maintain a constant distance d from each ship in front of and behind it. In the previous video, we derived the equations for the hyperbolic world line of the first of these spaceships, where the time ct is given by a hyperbolic sine, and position x is given by a hyperbolic cosine. The hyperbolic angle is given by the proper acceleration, alpha, divided by the speed of light c times the proper time tau. For reasons that will come up later, I'm going to rewrite this hyperbolic angle as alpha over c squared times c times tau. This spaceship accelerates with proper acceleration alpha and maintains a constant distance c squared over alpha from the origin behind it, which is also the Rindler horizon. We know that this distance is constant because when we calculate the space-time interval, s squared, which is ct squared minus x squared, and then take the square root of its negative value, we get a constant proper length c squared over alpha. I may sometimes write the equations of motion for an accelerated observer using d instead of c squared over alpha. D is the distance between the first spaceship and the Rindler horizon at the origin, and it's a convenient unit of distance to use when talking about distance in Rindler coordinates. I don't know if this distance d has an official name, so I'm just going to call it the Rindler distance. And we know that the proper acceleration is alpha because we can calculate the foreacceleration vector a by taking two time derivatives with respect to tau, and then taking the negative square root of a dot a, and we get alpha. So given that the distance between the rocket and the Rindler horizon is capital D, let's say that we want another accelerating rocket that maintains the same constant distance d from the first rocket. In other words, the second rocket must undergo proper acceleration and maintain a distance 2d from the Rindler horizon. We can do this by taking the equations of motion for the first rocket and dividing the proper acceleration alpha by 2. This means that the proper distance from the origin is now twice as big, 2 times c squared over alpha, or 2d, as desired. The forevelocity dotted with itself, u dot u, is c squared, as required. And the proper acceleration, the square root of negative a dot a, is now half as big, alpha over 2. So as we said before, in order for two accelerating spaceships to maintain a constant proper distance from each other, the spaceship in the back must accelerate harder, alpha in this case, and the spaceship in front does not accelerate as hard, alpha over 2 in this case. We can continue this pattern to get spaceships traveling with proper acceleration alpha over 3, alpha over 4, alpha over 5, and so on. All of these spaceships maintain a constant proper distance d from each other, but each spaceship must accelerate harder than the spaceships in front of it. When we have a collection of particles that accelerate together in such a way that the proper distances between them do not change, we call this Born rigid motion, after the physicist Max Born. And again, note that all of these spaceships have a common Rindler horizon located at the origin. We can take this collection of world lines for accelerating spaceships and use them to build a curvilinear coordinate system for spacetime. Taking the equations for constant proper acceleration, let's replace the coefficient in front, c squared over alpha, with a continuous variable x tilde. The x tilde variable lets us continuously choose a hyperbola with any constant proper distance from the origin of our choice, with this constant proper distance from the origin just being x tilde. We can also replace the expression c times proper time tau with a new time coordinate ct tilde. This time acts as a hyperbolic angle for the coordinate system and lets us pick a particular instant in time for all of the spaceships. These new coordinates, ct tilde and x tilde, form a curvilinear coordinate system that indicates how time and space are observed from the point of view of an accelerated observer with constant proper acceleration alpha, and whose Rindler horizon is at the origin. Unlike the standard spacetime coordinates, the Rindler coordinate system only covers a portion of our spacetime diagram, since accelerated observers cannot see anything beyond their Rindler horizon. The Rindler horizon line represents a line where the hyperbolic angle ct tilde approaches positive infinity. This lower diagonal line does not represent a horizon because light can cross through it, but it still represents a boundary of the coordinate system, where ct tilde approaches negative infinity. So now we have equations that change between the standard spacetime coordinates ct and x, and the new Rindler coordinates ct tilde and x tilde. In some ways, this is similar to the Lorentz transformations we've seen before, which also convert between two sets of spacetime coordinates. The difference is, this time, the new Rindler coordinates are curvilinear coordinates, and the transformation cannot be represented by a matrix multiplication. In this next part of the video, I'm going to state various properties of the Rindler coordinates that will help us understand how accelerated observers view spacetime. In particular, I'm going to show that all clocks on the different accelerating spaceships will tick at different rates. In other words, each spaceship measures a different proper time from the others. I'll also calculate the proper acceleration for each spaceship. And finally, I will show that the formula for the spacetime interval s squared from the origin does not depend on time. At the end of this video, I'll talk about how the speed of light can have values other than c in Rindler coordinates. The curves of constant x tilde are the curves of constant position according to an accelerated observer. These curves are a series of hyperbolic curves that all have the same Rindler horizon at the origin. Hyperbolas that are separated by equal proper distances at one point in time will maintain that same proper distance from each other for all time, just like the spaceships we saw before. The time coordinate ct tilde increases moving upward. The curves of constant ct tilde are actually straight lines that radiate from the origin. These are the lines of constant time. These show us where all the spaceships are located at any given moment along their journey. It's important to note that the t tilde coordinate is not the proper time tau. This means that t tilde is not the time measured by a clock on the spaceship traveling along a given hyperbola. The proper time tau measured by a particle on a hyperbola of constant x tilde is actually given by tau equals alpha over c squared times x tilde times t tilde. or equivalently, tau equals x tilde over the Rindler distance d times t tilde. I'll give a formal proof of this fact in Relativity 105 Part D, when I discuss proper time along curves, but here is some quick informal reasoning for it. Recall that given the equations of motion for the first accelerating spaceship with distance d from the origin, we got the equations of motion for the ship located at 2d by replacing alpha with alpha over 2 in the equations. If we rewrite c squared over alpha as d, this is the same thing as replacing d with 2d. If we compare the equations of the second ship to our general Rindler hyperbolas, we can see that ct tilde over d corresponds to c times proper time tau over 2d. Canceling the c's and the d's, we get that 2 times t tilde equals proper time tau. But we can also see that x tilde corresponds with 2d. So this factor of 2 is really the ratio between x tilde and d. Subbing this in, we get that the proper time tau for any spaceship of any position is x tilde over d times t tilde. So given this formula for proper time along curves of constant x tilde, this means that clocks located at larger x tilde values will tick more quickly. If we look at our 5 accelerating spaceships, on a line of simultaneity t tilde equals 1 second, we find that each spaceship has counted a different proper time on its clock. Even though all of these events happen at a simultaneous time for all the ships, we find the ships at larger x tilde values have measured longer proper times on their clocks. It's important to remember that the t tilde coordinate is equal to the proper time only for the first spaceship at x tilde equals d, and nowhere else. All the other spaceships will measure different proper times according to this equation. Also, the proper acceleration alpha is a parameter for the Rindler coordinates. There are actually several different versions of Rindler coordinates, each with a different value for the alpha parameter. Particles on a world line of constant x tilde will have a proper acceleration of c squared over x tilde, which is also equal to alpha times d over x tilde. To prove this, recall on world lines of constant x tilde that proper time tau equals x tilde over d times t tilde. We can use this to prove that d tau by dt tilde is x tilde over d, since x tilde is constant. And taking the reciprocal of both sides, we get that dt tilde by d tau is d over x tilde. If we start with the CT formula for Rindler coordinates and take the derivative with respect to proper time, we turn the sinh into a cosh and get a c over d term outside. We also get a dt tilde by d tau chain rule term. We don't take the derivative with respect to x tilde because we assume x tilde is a constant. Another derivative turns cosh back into sinh, and we get another c over d and another chain rule derivative term. Subbing in d over x tilde for the chain rule term, we can see that the d's cancel out, and we can also cancel one x tilde, and we end up with c squared over x tilde out in front. We can calculate the second derivative of x in a similar way. And calculating the proper acceleration, the square root of negative a dot a, we get c squared over x tilde, which is also alpha times d over x tilde. This formula basically means that the proper acceleration of each spaceship decreases as x tilde increases, which matches what we've seen. We showed in Relativity 104 Part E that the Lorentz transformation does not change the form of the formula for the spacetime interval s squared. All inertial frames calculate s squared by taking the time coordinate squared minus the space coordinates squared. But if we substitute in the Rindler coordinates for ct and x into the formula for s squared, we see that the formula for s squared in the Rindler coordinates has a different form that doesn't involve the time coordinate at all. This is because the Rindler coordinates are not obtained with a Lorentz transformation, and Rindler coordinates represent a non-inertial frame. So the formula for the spacetime interval looks different than what we're used to for inertial frames. Since the spacetime interval s squared doesn't depend on the time coordinate ct tilde, this means that the spacetime interval doesn't change with time for any of the spaceships traveling along the hyperbolas. And since the spacetime interval is always a negative number, negative x tilde squared, this confirms that x tilde is the proper distance from the origin at any point in the Rindler coordinate system. Each hyperbola is a curve of constant x tilde, and so it has a constant proper distance from the origin, or the Rindler horizon. As I stated before, the Rindler coordinates are only valid for a portion of the spacetime diagram. They only work for positive x, and when ct is between negative x and positive x in the standard coordinates. Now, these equations are a bit inconvenient because they are mostly useful for changing from Rindler coordinates ct tilde and x tilde to the standard coordinates ct and x. It's possible to invert these formulas to come up with new equations that change from the standard coordinates ct and x to Rindler coordinates ct tilde and x tilde. We've already seen that the spacetime interval, which is ct squared minus x squared in the standard coordinates, is minus x tilde squared in Rindler coordinates. If we multiply both sides of the equation by -1 and take the square root, we get a convenient formula for x tilde in terms of ct and x. We take the positive value of the square root since the Rindler coordinates work in the positive x tilde direction. Also, if we divide the formula for ct by the formula for x, we see that the x tildes cancel, and sin h divided by cos h is just the definition of hyperbolic tangent, tanh. We can eliminate tanh by using its inverse function, arctanh, on both sides, and then multiply both sides by c squared over alpha to solve for ct tilde. We now have formulas that convert from the standard coordinates to Rindler coordinates and back again. To summarize this video, we learned about Bell's spaceship paradox. If a set of spaceships accelerate together with the same proper acceleration, then the distance between the spaceships is constant when viewed from a rest frame. However, in the frames of the spaceships themselves, the spaceships will appear to be moving apart. Conversely, if the spaceships accelerate in such a way that the proper distance between them remains constant in their own frames, then each ship will have a different proper acceleration. The ship in the back will have to accelerate harder in order to keep up with the ship in the front. In this case, the stationary observer observes the spaceships moving closer and closer together. Both spaceships will have a common Rindler horizon behind them. In order to look at space and time from the perspective of someone undergoing constant proper acceleration, we derived the Rindler coordinates, which are curvilinear coordinates for spacetime. A traveler on a constant x tilde coordinate will have a constant proper acceleration of c squared over x tilde. The proper time for a traveler with constant x tilde coordinate is alpha over c squared times x tilde times t tilde. We also saw that the formula for the spacetime interval, s squared, was just negative x tilde squared, which is different than the formula that we're used to seeing in inertial frames. We also derived formulas to convert between the standard coordinates and the Rindler coordinates in both directions. The last thing I want to mention is that in Rindler coordinates, it's possible that the speed of light can be less than c or greater than c, where c is the speed of light in an inertial reference frame. However, it's important to note that the truth of this statement comes down to the definition of speed as dx tilde by dt tilde, which is not an invariant based on 4 vectors, and so different observers will disagree on it. The reason that this definition leads to the speed of light not being c is because t tilde is not equal to the proper time tau in Rindler coordinates, except in the special case of an observer that is located at the Rindler distance d. This observer will always measure the speed of light to be c when measuring light beams locally right next to them. The calculation of the speed of light to be not equal to c occurs for non-local regions of spacetime far from this observer, where the t tilde coordinate does not equal the proper time tau. In the future, with non-inertial coordinate systems and in general relativity, we will need to be very careful when interpreting spacetime coordinates, because unlike with inertial frames, the spacetime coordinates will not always have obvious physical meaning. So given the spaceships in the Rindler coordinates, let's find the speed of light in the Rindler coordinates dx tilde by dt tilde at various positions along the horizontal axis. The equations of these light beams in the inertial coordinates are x equals ct plus x naught, where x naught determines the initial position of the light beam along the x-axis. I'm going to go through this derivation quickly, so pause the video if you want to look at it more carefully. We know that the Rindler x tilde coordinate squared equals x squared minus ct squared in inertial coordinates. We can sub in the equation of our light beam, ct plus x naught, for the x variable. We can expand the square, cancel ct squared, and bring all the terms to one side, and replace ct with x tilde times sinh of ct tilde over the Rindler distance d. Since this is just a quadratic in terms of x tilde, we can use the quadratic formula to solve for x tilde. This 1/2 cancels with this 2 and the 2 squared and 4 under the square root sign. We can also factor out x naught to the front of the expression. The fundamental hyperbolic trig identity tells us that 1 plus sinh squared equals cosh squared. And we're going to enforce that x tilde is positive to get the positive square root sign. It can also be shown that sinh plus cosh equals the exponential of the hyperbolic angle. So we have a formula for x tilde, and if we take the derivative with respect to t tilde, we get c over d times x naught times this exponential. If we restrict this formula to the horizontal axis, where ct tilde equals 0, then we get the speed of light is c over d times the initial position x naught. This means that a beam of light sent from the Rindler distance d has a speed c. A beam of light sent from the position 2d has a speed 2c. A light beam sent from 3d has speed 3c, and a light beam sent from 4d has speed 4c. Also, a light beam sent from 1/2d has speed 1/2c. And a light beam sent from the Rindler horizon at the origin has 0 speed, as we discussed in the last video. So on the horizontal axis, at the Rindler distance d, the speed of light in Rindler coordinates dx tilde by dt tilde is equal to c. As we can see, this light beam travels 1 grid unit of distance in 1 grid unit of time in this grid box. For distances less than the Rindler distance d, the speed of light is less than c. A beam of light travels less than 1 grid unit of distance in 1 grid unit of time. And for distances greater than d, the speed of light is greater than c. A beam of light travels more than 1 grid unit of distance in 1 grid unit of time. So this idea that the speed of light might not be equal to c can seem pretty confusing. So how do we interpret this? Remember, the second postulate of special relativity says that the speed of light in a vacuum, c, is the same in all inertial frames. This means that, in an inertial frame right beside a light beam, the frame will always measure light as having a speed of c. So whether we're in a global inertial frame or an instantaneous inertial frame at one instant along a curved world line, we'll measure the speed of light right beside us to have speed c. And what we're really saying here is that the derivative of proper length with respect to proper time at a given point is always c for a light beam's world line, where the proper length and the proper time are measured according to inertial frames. However, it's very important to realize that the clocks in non-inertial frames can tick at different rates. This means that non-local beams of light can have a speed different from c, because its speed is being measured with a non-local clock. Mathematically, this means that the derivative of proper length with respect to proper time for a light beam is not necessarily equal to the derivative of the space coordinate with respect to the time coordinate for a non-inertial coordinate system. Let's visualize this with space-time diagrams. In inertial coordinates, we know that along lines of constant position, the proper time tau is just equal to the coordinate time t. So if we place clocks tau1, tau2, and tau3 at various positions and set them all equal to 0, then at this line of simultaneity a bit later, the clocks all read the same value of 1. So in inertial coordinates, the coordinate time t is equal to the proper time tau if we remain at a constant position. And this is the same time measured for all positions x. However, in Rindler coordinates, we know that along curves of constant x tilde, the proper time along each curve depends on the position x tilde. So if we start clocks tau1, tau2, and tau3 at 0 at various positions, then at this next line of simultaneity, they will all read different times, because more proper time passes at larger x tilde positions. Clocks in Rindler coordinates will tick at different rates depending on their position, and so the coordinate time t tilde is not always equal to the proper time tau for a given location. It's also worth mentioning that in global inertial frames, the position coordinate is equal to the proper length along lines of constant time. And this is also true in the Rindler coordinates as well. The important thing to note is that the coordinate time t tilde is not equal to the proper time in Rindler coordinates. If we return to our 5 spaceships, along the line of simultaneity at t tilde equals 1, the first spaceship at position d counts a proper time of 1 on their clock. But according to our formula, the fourth spaceship at position 4d counts 4 units of proper time on their clock. A beam of light next to the first spaceship will have a speed in Rindler coordinates of dx tilde by dt tilde, which is just dl0 by d tau1, which is the ship's local proper time. As stated before, the local speed of light in an instantaneous inertial frame is always c. If we measure the local speed of light at the fourth spaceship using the local proper time tau4, we also get a speed of c, because this is also an instantaneous inertial frame. However, if we measure this light beam at the fourth spaceship using the Rindler coordinates dx tilde by dt tilde, we're not measuring this light beam using a local clock, since 1 unit of t tilde time is only equal to 1/4 of the local proper time tau4 on the fourth rocket. The result is that we get the speed of the light beam to be 4c, because it was measured with a non-local clock. So the important points to remember for non-inertial frames are that the spacetime coordinates don't always have obvious physical meaning. It's possible that the coordinate time is not always equal to proper time along lines of constant position, and it's possible that the coordinate position is not always equal to proper length along lines of constant time. Therefore, the local speed of light beams is not always equal to the coordinate speeds of light beams measured non-locally. Now, all of this might seem pretty confusing. To understand this better, we're going to study the Jacobian matrix and the Rindler metric for getting proper time along curves in the next couple videos.